To maintain a non-separately derived system and the neutral ground bond in a building, install a fourth conduit between the transformer and building containing a 350 kc mil copper ground conductor. Use a 3-pole 4-wire automatic transfer switch, also known as an ATS, with a ground fault relay. Install a grounding electrode at the building and bond the grounding electrode to the neutral bar. The requirement for ground fault protection applies to feeders with overcurrent protection rated 1000 amps or greater. If the service feeder exceeds 1000 amps, ground fault protection is required. Install an ATS with a ground fault relay that trips the feeder breaker in the event of a ground fault. It is possible to monitor for ground faults at the building panel and use a shunt trip device to trip the feeder breaker at the ATS. The 7 sets of 4/0 copper cables that are currently in place may not be sufficient to carry the additional load of the ground conductor. It may be necessary to upgrade the cable size or add additional cables. Ensure that the conduits have sufficient space to accommodate the additional ground conductor. Coordinate the shunt tripping device with the ATS ground fault relay to ensure proper operation. National Electrical Code, also known as NEC Section 230.825, allows for the ATS to be upstream of the building's main disconnect if certain conditions are met. NEC Section 250.142. A1 allows for a neutral ground bond at the building if the system is non-separately derived. NEC Section 250.122. F2 allows for a ground conductor size of 2/0 American wire gauge, also known as AWG, for feeders over 1000 amps. Let's delve deeper into these aspects. Firstly, consider the implications of running a separate grounding conductor. The 350 kc mil copper ground conductor in its own conduit provides a dedicated, low impedance path for fault current back to the source, which is essential for effective ground fault protection. This method ensures that any fault current has a clear and rapid path, facilitating quick operation of overcurrent protective devices and minimizing potential damage. Secondly, the selection of a 3-pole 4-wire ATS with ground fault relay is crucial. This configuration allows for the switching of all 3 phases and the neutral conductor, while the ground fault relay monitors the current balance between these conductors. If an imbalance is detected, indicating a ground fault, the relay will trip the feeder breaker, isolating the fault and preventing further damage. The neutral switching capability of the ATS is also important for maintaining the integrity of the neutral ground bond in the building. Thirdly, establishing a grounding electrode system at the building and bonding it to the neutral bar is a fundamental safety measure. This bond ensures that the building's electrical system is referenced to earth potential, minimizing the risk of electric shock. The grounding electrode system typically consists of ground rods, metal underground water pipes, or concrete encased electrodes, all interconnected to provide a low impedance path to earth. Next, regarding the ground fault protection requirements, the NEC mandates ground fault protection for solidly grounded wire electrical services of more than 150 volts to ground, but not exceeding 1000 volts phase to phase for each service disconnecting means rated 1000 amps or more. This requirement aims to reduce the likelihood of destructive arcing faults, which can occur when a phase conductor comes into contact with ground. The ground fault protection system must be designed to trip the service disconnecting means within a specified time frame, typically less than 1 second, to minimize the duration of the fault and reduce potential damage. The ATS with a ground fault relay serves as the primary means of providing ground fault protection. The relay continuously monitors the current flowing in the phase conductors and the neutral conductor. Under normal operating conditions, the sum of these currents should be 0. However, in the event of a ground fault, a portion of the current will return through the grounding path, creating an imbalance that is detected by the relay. When the imbalance exceeds a predetermined threshold, the relay will trip the feeder breaker, isolating the fault. The ability to monitor for ground faults at the building panel and use a shunt trip device to trip the feeder breaker at the ATS provides an additional layer of protection. This approach allows for faster fault detection and isolation, as the monitoring system is located closer to the potential fault location. The shunt trip device is a remotely operated mechanism that can trip the feeder breaker upon receiving a signal from the monitoring system. This can be particularly useful in large or complex electrical systems where a ground fault may not be immediately apparent. When evaluating the cable ampacity, it is essential to ensure that the existing conductors are adequately sized to carry the additional load imposed by the ground conductor. The NEC provides tables that specify the ampacity of conductors based on their size, insulation type, and installation conditions. Factors such as ambient temperature, conduit fill, and conductor bundling can also affect the ampacity of conductors. If the existing conductors are not sufficient, it may be necessary to upgrade to a larger size or add additional conductors to meet the load requirements. The conduit fill requirements are outlined in the NEC, which specifies the maximum percentage of conduit cross-sectional area that can be occupied by conductors. This is to ensure adequate heat dissipation and prevent damage to the conductors. When adding a ground conductor to an existing conduit, it is important to verify that the conduit fill limits are not exceeded. If necessary, a larger conduit may be required to accommodate the additional conductor. Coordinating the shunt tripping device with the ATS ground fault relay is crucial to ensure proper operation and avoid nuisance tripping. The coordination study should consider the time current characteristics of both devices to ensure that the shunt trip device operates before the ATS ground fault relay in the event of a fault at the building panel. This will minimize the duration of the fault and prevent unnecessary interruption of power to the entire system. In relation to NEC section 230.825, it allows for the ATS to be installed on the supply side of the service disconnecting means under specific conditions. These conditions typically involve the ATS being equipped with features that ensure the integrity and safety of the electrical system, such as overcurrent protection and isolation capabilities. This arrangement can be advantageous in situations where the ATS needs to be located closer to the power source for space or aesthetic reasons. Considering NEC section 250.142 A1, it permits the neutral conductor of a non-separately derived system to be bonded to the grounding electrode system at the building. This bond establishes a common reference point between the neutral conductor and ground, minimizing the potential for voltage differences and reducing the risk of electric shock. However, it is important to note that this bond is only permitted in non-separately derived systems, where the neutral conductor is directly connected to the power source. And lastly, NEC section 250.122 F2 provides guidance on the minimum size of the equipment grounding conductor for feeders. For feeders rated over 1000 amps, the equipment grounding conductor must be sized no smaller than 2/0 AWG copper or 4/0 AWG aluminum. This requirement ensures that the equipment grounding conductor has sufficient capacity to safely carry fault current back to the source. When dealing with a service that involves 7 sets of 600 kcmil conductors, several factors need careful consideration. Firstly, the physical arrangement and termination of these conductors at both the transformer and the building service entrance can be complex. Ensuring proper termination techniques and maintaining equal current sharing among the conductors are critical for reliable operation. Secondly, the overall ampacity of the service must be carefully calculated to ensure that it meets the building's load requirements. The ampacity of each 600 kcmil conductor must be derated based on factors such as the number of conductors in a raceway and the ambient temperature. Thirdly, the coordination of overcurrent protective devices, such as fuses or circuit breakers, is essential for protecting the service conductors from overload and short-circuit conditions. A coordination study should be performed to ensure that the protective devices are properly sized and coordinated to minimize the extent of any fault and prevent unnecessary interruptions of power. The location of the generator and ATS 300 feet away from the building presents both advantages and challenges. One advantage is that it can free up valuable space within the building and improve aesthetics. However, it also introduces challenges related to voltage drop and coordination of protective devices. The voltage drop in the service conductors must be carefully calculated to ensure that the voltage at the building service entrance remains within acceptable limits under all load conditions. If the voltage drop is excessive, it may be necessary to increase the size of the conductors or install voltage boosting equipment. The coordination of protective devices must also take into account the impedance of the service conductors, as this can affect the magnitude of fault current and the performance of the protective devices. The ground fault protection system should be tested and maintained regularly to ensure its proper operation. Testing should include verifying the sensitivity and response time of the ground fault relay, as well as the operation of the shunt trip device. Maintenance should include inspecting the grounding connections and conductors for corrosion or damage, and replacing any components that are not functioning properly. Additionally, keep accurate records of all testing and maintenance activities to demonstrate compliance with applicable codes and standards. Finally, remember that electrical work can be dangerous, and it is essential to follow all applicable safety procedures. Wear appropriate personal protective equipment, such as safety glasses and gloves, and de-energize all circuits before working on them. If you are not qualified to perform electrical work, hire a licensed electrician.